At the beginning of this series of videos, I skipped over neural networks and said that we'd talk about it later. So let's go into neural networks now. They're a method that involves multiple layers of regression that take matrices and vectors and then put out the best fit matrices and vectors that then are passed through the next layer. Now, actually, through much of what we've been doing, we've been using them behind the scenes, and that's all part of the language automation to use these for things like the feature extraction. But we can wield them much more precisely by actually specifying the shape of the network that we use. So the language provides a collection of layers that are a symbolic representation both of the action of the layer, and they also hold all of the parameters that we need to fit, that we're trying to tune to make best predictions, and information about what comes in and what goes out. I don't have time to explain any of these different layers. Some of them are quite straightforward. They simplify, or they pick out features, or they reduce the dimensionality. And the idea is that one joins them together into a sequence where one feeds into the next. Not necessarily linearly. They could be a complicated graph that crisscrosses, and you can even have recurrent networks that feed backwards into themselves. Now, we don't have time to talk about how to make these from scratch, but that doesn't mean you can't use them anyway without having to have the knowledge on wielding each of these layers individually. Now, one way of dealing with that is that we're providing a library of pre-built networks. So this net model command here allows me to download a network that is, in this case, the LeNet trained on MNIST data. So this is a neural network that is used for classifying handwritten digits and characters to try and predict what the digit is. And this is the symbolic description of that network. So it's got 11 layers. It starts with an input, ends with an output, and it goes through different layers along the way. And if we click on one of these layers, we can find out more information about the details of what it does and what its current settings are. And we can use that directly. It's already pre-trained this network on an image. This is a picture of a 0, and then it's made a prediction that it's the character 0 from that. But one of the things we can do with this is we can retrain that network. So I might not understand how this network works, but that doesn't mean I can't work with it. So I can take that network that we've just downloaded, and I'm going to add some new data to the network. So let me just run this current image command here and hold up a finger into the picture, and it's now grabbed something from my webcam here that is me holding up a finger, and I'm going to tell it that that represents a 1. So now when I run that training, it's going to take what it already knew, the current state of the trained network, and it's going to try and re-optimize it in light of the data that it already knew. So this is really just a much richer version of classify. I've got my input and my output, just like we were classifying before, but now I'm specifying the exact shape of neural network that we're going to try and train. And this isn't a terribly rich neural network, but it's now retrained that so that we can use it with the new knowledge that it's had embedded in it. So if I ask for that new network to be applied to the 0, we get the same value. But if I put in here, for example, another image that of me, then it makes a prediction that that's a 1. Now, it's not doing anything terribly clever here because it's probably the only image that it's got that has a big complicated mess of colors in it. And so that's a fairly easy thing to train against. But perhaps if the network is rich enough and enough data, we could start training it to be able to count the number of fingers I'm holding up. Of course, that depends on this being rich enough to be able to describe all of the scenarios that it's used for. And that's why there's a whole collection of these different models that have been built by researchers for different types of application, and why you need to be able to produce your own. Now, these models that we're downloading have a full symbolic representation in terms of all of those layer objects that I showed you a moment ago. And one advantage of that is we can treat that just like any other piece of data within the Wolfram language, because the Wolfram language has no problem handling symbolic objects. So one use of that, for example, is to build new networks that use existing networks just as components within a much more complicated set of layers. Another thing we could do is reach inside the symbolic object and find out things about its state. Let's look at an example of that in action. So here is a another one of our library of models. This is actually the model that's used behind the image identification that we looked at earlier, with the spotting teapots and teacups in images. And you can see it's a bit more of a complicated model. And in fact, some of these layers themselves, if we drill into those, have sub-layers within them. So it's much, much richer and more expressive, which is why it's capable of image identification more than just digit identification that we did a moment ago. So the outcome is that I can apply that to a picture, and it can figure out what's in the picture out of the big training set that it's been given. But one thing I can do is I can just take part of that, I can transform the thing and make a simplified version of the model. And so here are the first 10 steps of that model. Now, we haven't got to the end of the process, and so we're not going to be able to use it to identify. All we'll see is what layer 10 is seeing within the image. So I can apply that to the tiger, and we're going to get matrices out. So I'm going to ask each of those matrices to be turned into an image. And what we see is effectively the insides of the brain of the neural network at layer 10. And we can jump through this at different layers and see how the images are being progressed. That maybe at layer 2, it's doing some basic transformations, but by layer 15 or so, maybe things are starting to become a bit more abstract, and it's no longer possible to see these as images, but maybe these start representing concepts or key features that are going on. So it's possible to start tracing through the network which neurons are dying out and becoming uninvolved in a particular image, and which are doing something useful and lighting up and being excited. And so, for example, if I compare that to a picture of broccoli going through the same 10 layers, and we compare some of these side by side, we'll see that at some point they start diverging in their interpretation. So there are quite sophisticated things you can do because you have the full description layer. But you do need to know something about what these layers mean to be able to do the most important stuff.